Hello and welcome to MeduHub. I am Neha Gupta from the chemistry faculty. Today we will be discussing the factors which affect the Sn1 and Sn2 mechanisms in alkyl halides. So substitution nucleophilic 1 or 2. The factors which affect Sn1 or Sn2 or which one out of the two will take place are the type of alkyl halide, the type of nucleophile, and the type of solvent used. Under type of Rx, we can consider two factors. One is the polar factor and other is the steric factor. Let us discuss the polar factor first. So for this, let us consider a series of molecules. We have an ethyl halide, then we have an isopropyl halide, CH3, X, and then we have a third butyl. This is isopropyl. We have a third butyl halide where C, CH3. There are 3 methyl groups. So halide. So this is 1 degree, this is 2 degrees, and this is 3 degrees. Now imagine Sn2 mechanism is taking place because of CH2. Now CH3 group has a strong plus I effect. This means that it is going to donate its electron density, which will make this alpha carbon electron rich, right? So here just one CH3 group is there. In isopropyl there are 2 CH3 groups, so electron density of the alpha carbon will be more. In third butyl there are 3 CH3 groups and the electron density on this alpha carbon will be the maximum out of these 3. So when Sn2 mechanism is taking place, the nucleophile directly attacks the alpha carbon. If the alpha carbon is electron rich, the attack by this nucleophile will be hindered. So this follows that the attack would be easiest in a 1 degree halide. It will become more difficult as you move from 1 to 2 to 3 degree halide. So we can safely say that for an Sn2 mechanism, the rate of the reaction follows an order, largest in 1 degree, then 2 degree, and then 3 degree. Now let us see what will happen if we talk about an Sn1 reaction. In Sn1 reaction, there is a carbocation formation. For that, the first step is ionization of the alkyl halide to give a carbocation and the halide ion. Again, going by the same logic, CH3 group has a plus I effect. Because of one CH3 group, the electron density on this will increase. Then the polarizability of this carbon-halogen bond will increase and this will be easier to break. Here the electron density on this carbon will be more than the 1 degree carbon. This bond will be more polarizable. This bond will be further easier to break. And similarly, this one will have the maximum electron density on this carbon, and because of the electronegative nature of this halide ion, this electron density will shift here and this bond will be the easiest to break. There is another way to understand this. Let's say all these carbocations are formed. This is a 1 degree carbocation, this is a 2 degree carbocation, and this is a 3 degree carbocation. So we know from logic that because of the plus I effect, a 1 degree carbocation is the least stable of all. Right? So it follows that for an Sn1 mechanism, it is the easiest to form a 3 degree carbocation. A 3 degree carbocation is the most stable. So the order of the reaction will be 3 degree greater than 2 degrees is greater than 1 degree. Right? Now we need to see the steric effects. In an Sn1 mechanism, let us see, let's say there is a carbon with A, B, B, and a halogen group attached here, right? There are 4 groups attached. For an Sn1 mechanism, if these 3 groups are very bulky and the nucleophile has to attack this carbon, there's going to be a lot of crowding around this carbon which will resist the impact of the attack of this nucleophile on this carbon, right? Because all these groups will have to compress and move so that OH minus can come attack this carbon. And in the transition state, there are going to be 5 atoms of groups simultaneously attached to this carbon. So because of overcrowding, this attack will be somewhat hindered. This again follows that it is easiest for an Sn2 mechanism to take place in a 1 degree halide and most difficult in a 3 degree halide. But what happens in the case of an Sn1 mechanism? In Sn1 mechanism, this alkyl halide will assume a trigonal shape when it forms a carbocation. Right? This is a carbocation. So because now it has only 3 groups attached to the carbon, it can somewhat relieve this strain. So steric hindrance does not play that big a role in an Sn1 reaction. So now we know how the structure of Rx affects an Sn1 or an Sn2 reaction. The nature of the X group does not really affect the mechanism of the reaction, but it affects the rate of the reaction. It has been found that the rate follows this order: Ri, greatest, Rpr, then RCl, and Rf. So majorly the type of the reaction is determined by the type of R group. Now what happens when we change the nucleophile? So in case we have a strong nucleophile, that is a nucleophile which has a very strong nucleophilic activity, or a strong base that is highly electron rich, this will directly attach the substrate, that is Rx, and proceed via an Sn2 mechanism. Because the nucleophilic activity of this nucleophile is more, it will not wait for the substrate to become a carbocation, but it will directly attack the alpha carbon and form the product. But in the case of a weak nucleophile or a weak base, this will have less affinity for attachment to the Rx. So what will it do? It will wait for Rx to dissociate into a carbocation, and then it will attack this carbocation to form the final product. This means a weak nucleophile favors an Sn1 reaction. So let us now see how the type of solvent affects the mechanism of the reaction, whether it's going to be Sn1 or Sn2 based on the type of solvent. Let us take a polar protic solvent. What is a polar protic solvent? This is a solvent which has a dipole moment, a net me, and it has a hydrogen attached to an electronegative atom, because of which this is protonic, this hydrogen is protonic. In the case of a polar protic solvent, let's take an Sn1 mechanism where a carbocation is formed and the halide ion leaves, right? Polar protic solvents are ethanol or water. So what will happen in the case where water is the solvent? We have this solvent surrounding the carbocation and the solvent surrounding the halide ion. Each. So because of a slight negative charge here, slight positive charge here, this oxygen will have dipole-dipole interactions with the carbocation here. This means that the interaction between the solvent and the solute will be more, and this will be solvated and hence stabilized. Similarly, this leaving halide ion will also form hydrogen bonds with the hydrogen of this solvent molecule, that is water. Here, this has slight positive charge, oxygen has a slight negative charge. So halide ion will also be solvated. So more is the interaction between the solvent molecules and the ion, more will be the solvation, more will be the stability. So in case of an Sn1 mechanism, the reactant is Rx, which will not be solvated because it is not polar, and the transition state products are more polar in nature. They have a high charge density and they will be stabilized. This will lead to an overall decrease in the activation energy of this step, and hence an Sn1 mechanism will be favored. What happens if we use this polar protic solvent like ethanol or water in the case of an Sn2 reaction? In an Sn2 reaction, the reactant gives a transition state where we have OH, say X, and there are 3 groups attached to this carbon. So there are slight negative charges here and a slight positive charge here in the transition state, and the reactant is Rx and a nucleophile. Now the charge on the reactant, which is the nucleophile here, is more concentrated, whereas the charge on the transition state is more dispersed over the entire molecule. So the solvent will be able to solvate this more than the transition state. Now if the reactant is getting more solvated than the transition state, the activation energy for this overall reaction will be increased, which will lead to a hindrance in the reaction proceeding via Sn2 mechanism. So we can safely say that in case of a polar protic solvent, an Sn1 mechanism is favored, whereas if the solvent is polar protic, an Sn2 mechanism will not be favored. Sn2 mechanism takes place in the case of polar aprotic solvents. That is the solvents which do not have a proton but they still have a dipole moment for solvation. Examples are acetone or dimethyl formamide, COH and CH3 DMF or DMSO, dimethyl sulfoxide, S+CH3CH3. So in case of a polar protic solvent like C2H5OH, H2O, an Sn1 mechanism will take place, and in case of a polar aprotic solvent like DMF, DMSO or acetone, an Sn2 mechanism will be favored. So let us summarize what we learned today. We discussed the factors affecting Sn1 and Sn2 mechanism. The first factor is the type of alkyl halide. So a 1 degree, 2 degree or 3 degree alkyl halide determines whether a reaction is going to be Sn1 or Sn2. In case of a 1 degree halide, an Sn2 reaction is favored. In case of a 3 degree, an Sn1 reaction is favored. There is a special case here in the case of an allylic or a benzylic halide. Let us discuss it. This is an allylic halide and this is a benzylic halide. So prima facie, if you look at these two, both of these are 1 degree halides. So you would suggest that they would undergo an Sn2 mechanism to have a nucleophilic substitution reaction. But there is a special stability attached to the carbocations which are formed in these two cases. The carbocation formed will be somewhat like this, and these will be resonance stabilized. So this will give us the positive charge here and the negative charge here. And similarly, a benzylic halide will give a carbocation which is again resonance stabilized. This one moves here and we get a positive charge on this carbon, a double bond here, and so on and so forth. So because of the special resonance stability associated with these two, even though they are 1 degree primary halides, allylic and benzylic favor an Sn1 reaction. Next we discussed the type of nucleophile. So we saw that if it is a strong nucleophile, it will favor an Sn2 reaction, and a weak nucleophile favors an Sn1 reaction. And the type of solvent also affects the mechanism of the reaction. If we have a polar protic solvent, it favors an Sn1 reaction, and a polar aprotic solvent favors an Sn2 reaction. Okay? Thank you so much for watching. I'll see you in the next video.